Hello. So what we're going to be talking about today is Riemann sums and what a definite integral is. So this is just a continuation of what we've been talking about with sums and finding the area under curves and going all the way back to what an indefinite integral is. Now we're going to learn more about another type of integral. So now what's on your screen is this big, long, scary looking definition, and all it is the definition for what a Riemann sum is, which we kind of mentioned in the last video about sums and area under curve and LRAM and RRAM and all of that. So what the definition says is if you let f of x be defined on the closed interval from a to b, and you let delta, which is what this triangle symbol is, it's the Greek letter delta, be a partition of a to b. So partition just means that it splits up the interval. So we'll just start translating this from math speak into normal people speak. So if you're splitting up your interval of a to b, and each of your delta xi's, so that's just going to be the width of the ith subinterval, whereas that kind of looks like the delta x that we were talking about before with sums, but before, whenever we talked about delta x, it meant that all of the delta x's across the interval were the same, whereas delta xi's, they don't have to be the same. They can vary as you go across the interval and all of that. So they could all be different, they could all be the same, it doesn't matter. So in other words, so now if you take CI to be a point in any of the ith subintervals, so CI is going to be in this interval right here, then the sum from I going from 1 to n of f of CI times delta xi for all of the CI's in that interval, that's just called the Riemann sum for the partition. Now that seems really complicated, especially because you haven't been dealing where you can let delta xi vary. But for our case, we're just going to let delta x be the same thing that we've always let it be. We're just going to still let that delta x be b minus a over n quantity. But this is just talking about different types of sums that you could have, anything like that. We don't really use this definition too much because we can use the sums that we've been using, which are Riemann sums. They're just where the delta x is equal to the same thing across the interval. We're just going to continue using that because when we're going to start taking the limits of these things, and when you take the limit, all of the answers come out to be the same no matter what your delta x's are. So now we have another definition, which is when we're going to start taking the limit as n goes to infinity. So if we take our normal sum, which is what this is right here, and if instead of putting a fixed number n on the top, so instead of putting in like 4 or 5 or 6 or whatever at the top of your n for how many rectangles you should be constructing, if we just put an n there, and then take the limit of the sum as we let n go to infinity. So as we split the interval up into more and more rectangles, as we take that limit, we get this funky looking integral sign over here. So we get the integral from a to b of f of x dx. And this right here is your definite integral. So before we were doing indefinite integrals, where we were just doing the integral of a function over the whole real number system. So we were just finding a general antiderivative for it. But when we take a definite integral, instead of getting a function out of it at the end, we're actually going to get a number out. And so there are a few different parts of this integral that you need to know the names of. So A is what we call your lower integration limit, or your lower bound of integration, and B is your upper bound. So we'll call that the upper integration limit, or the upper bound of integration. So instead of looking at the whole real number line or the whole domain of this function, we're instead going to be looking at what is going on between points A and B on f of x. And so now we're just going to do an example problem and show how that works out. So now what we want to do is we want to evaluate the definite integral from -2 to 1 of 2x dx. And notice that whenever I read off a definite integral, you always start with the bottom and then read towards the top. So it always goes from bottom to top, which is something that you want to remember when we start talking about a shorter way to evaluate definite integrals. So we can rewrite this definite integral to just be the limit as n goes to infinity from I going from 1 to n of f of xi times delta x. So now we're just going to evaluate this sum just like we did before. So we need to figure out our delta x first of all, and then we need to figure out how to write our xi's and plug them into the function. So just like we just mentioned, our delta x, we're just going to let that be b minus a over n. But this time we're not going to have a number to plug in for n, so we're going to have n's in our answers, which is fine. So b in this case, just quick label them. A is always the bottom one and b is always the top. So b is going to be 1 minus a negative 2 over n, which is just going to give us a 3 over n. So now we just need to figure out how we want to plug in. So one thing that might help us here is if we draw a quick graph from negative 2 to 1 of this function f of x equaling 2x. And I know that f of x is equal to 2x because f of x is always just the quantity that's directly before the dx. So let's see, if we plug in 0, we get 0. If we plug in 1, we're going to get 2. Negative 1, we're going to get negative 2. And we plug in negative 2, we're going to get negative 4. So we're looking at the sum over this interval. So why don't we do right-handed sums? And so we're just going to set it up as the right-handed point. So we're just going to draw some rectangles. So what we're going to do is we want to do the right endpoints. So we're going to have points here. Let's do them in a different color. Here, 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 and so on. So whenever you have right-handed limits, we remember from doing our RRAM example that you plug in a, so we're going to plug in negative 2 plus delta x, which is 3 over n, and we're going to multiply that by I. And then we're going to just plug in for delta x again, so we're going to get 3 over n. So now what we're going to do is we're going to evaluate the sum first, and then we're going to take the limit as n goes to infinity once we have a nice answer. So we're just going to copy our sum down here. So instead of just doing f of negative 2 plus 3n over I, let's actually plug that in so we can get rid of the f. So f was 2x, so we're going to have 2 times negative 2 plus 3 over ni times 3 over n. Now, the indexing variable in this sum is I, so n's are technically a constant here. So we can pull out n's and anything like that. So now we can go through and simplify. So if we simplify, we're going to get the sum from 1 to n of negative 4 plus 6 over ni times 3 over n. 3 over n is a constant, so let's pull that out front. So now we're going to get the sum from negative 4 plus 6 over ni on the inside. We're going to use our summation properties now, and we're going to split this up into two sums. So we're going to have the sum from 1 to n of negative 4 plus the sum from 1 to n of 6 over ni. Okay, so now you might remember from the summation videos that we have another property where if we have any constants inside of our sum, we can pull them out front. So we can leave the negative 4 in here because that's just going to be the sum of a constant. But for this second one, we have an I in there. So we want to make it so it's just the sum of I, so it's really easy for us to plug in using our summation formulas. So we're going to pull that 6 over n out front. So we just have the sum from 1 to n of I. So that way it matches up with a summation formula. So now all we're going to do is we're going to plug in. So we're going to move over here so we have some more room. So the sum of a constant is from 1 to n is just going to be the constant, so negative 4 times n plus 6 over n. And the sum from 1 to n of I is just going to be n times n plus 1 over 2, just plugging straight in for that formula for the sum of I. So now all we have to do is simplify. So before we multiply this 3 over n in, we want to simplify as much as we can on the inside. So notice that when we multiply the 6 over n by the summation formula, we have an n in the denominator out here, and we have 1 in the numerator up here. So we can actually cross those out, and we can also cross cancel between the 2 and the 6 and make this a 3. So now we really just have 3 times n plus 1, so we're going to get 3n plus 3, which is just going to be equal to 3 over n times negative n plus 3. And now if we simplify through, we're going to get negative 3n over n plus 9 over n, which is just going to be equal to negative 3 plus 9 over n. So now that we know what our sum is equal to, what we're going to do to evaluate the integral from negative 2 to 1 of 2x dx, we're going to take the limit as n goes to infinity of negative 3 plus 9 over n. So when we take the limit as n goes to infinity, the limit of negative 3 is just going to stay negative 3, but 9 over infinity is going to go towards 0. So we're going to get negative 3 plus 0, which equals negative 3. So that's going to be the value of the definite integral from negative 2 to 1 of 2x dx. So it's always going to be the same sort of format for any of these problems when you're using the summation definition to solve a definite integral. You're just going to set up your sum, and instead of putting a number in for n, you're going to just leave it as n. You're going to set up your rectangle sum, so you're going to find your xi and your delta x. And if you're having trouble figuring out how to write your delta x, I'm sorry, not your delta x, your xi's inside of your function, like we did all the way up here by plugging this in, because this was our xi. So if you're having trouble figuring out how to write that yourself, just draw a picture and draw a finite number of rectangles and figure out if you want to do it with the left endpoints or the right endpoints. I think the right endpoints tend to be a little easier because if it's the left endpoints, you actually have to plug in, instead of having 3n over times I, we would have had, so this was with your right, so your RRAM. If you were doing LRAM, you would have f of negative 2 plus 3 over n times I minus 1 times your delta x, which that just means you have an extra step of foiling and simplifying and all of that. So it just makes things, I think, a little bit more complicated in most cases. I know I'm partial to the right Riemann sum approximations, just like we were talking about last time. So if you're ever having trouble, just draw a finite number of them and figure out how you would define them with the finite number. And then instead of plugging in for whatever value of n you picked, just plug in an n instead, and it should work out just fine. But if you were to do this problem using the left endpoints, you would get the same answer at the end. So it doesn't matter if you're going to use your right endpoints or your left endpoints of your rectangles, it's still going to get the same answer once you take the limit as n goes to infinity. Okay, so thank you so much for watching. I hope this helped clarify some things about definite integrals for you. Have a great rest of your day.